Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Welcome again into this TV listening program. I'm teacher Jean-Marie. I hope you still remember me. I'll be teaching you physics for all of the senior 60 classes. Now, student, remember to take your physics notebook to write down some explanations and exercise notebook and calculators to perform some of the given work activities. Now, students, today we are going to continue with the Unit 5. Do you remember where we have stopped? And this Unit 5 is the atomic nuclei and radioactive decay. Okay, students. The unit that we have is not new because the last time we have introduced it. So I'm going now to give you a simple question. Now, students, what is the relationship that is between the following element that I'm going now to give you? I want you to give me one word which expresses the relationship. So give one word explaining or describing the relationship between the following elements. So, number one, we have carbon 12, that is 6, and carbon 14. So, what is the relationship? One word only. Okay, students. Now, one word that we have expressing these two elements is, these elements, they are isotopes. These elements are isotopes. Now, why am I having now to come back on these two elements or on this word? Because today I want now to start with a new lesson, and the title is the working principle of a mass spectrometer. Okay? So today we have working principle of mass spectrometer. Now, what is the mass spectrometer? Let's define this. So this is the point one for this one. Now, what is the definition? How can we define this mass spectrometer? Yes, students. So mass spectrometer, as we define, it is a device that is used to separate the charges of the different masses, okay? Now, here we have a device used to separate the charges of different masses. But we can't only say a device used to separate the charges of different masses. Again, there is another way that we can explain this mass spectrometer. A mass spectrometer, again, is used to just to explain the difference between the two isotopes. That's why now we had now to again to introduce the edition of today, starting by the isotope as a word. So here we have again use it to describe the charges, the charges and masses of isotopes. Okay, students. So let's now have the explanation of how now this mass spectrometer really works. So let's see. First of all, we have a diagram. So the diagram is similar to this one, but I'm going now to explain to you how this diagram really is going now to be used now to just to separate the two isotopes, or the masses of the isotopes. So here we have a ionization chamber. The ionization chamber is what we have here, and this is where we have a gas, okay? And then we have the vacuum chamber, this one, okay? So this also is a velocity selector, right? Okay, now students, as what you see, at the first time we have a gas, and then we have the ions. They are now ejected, they are emitted from this ionization chamber, and then they are sent to the cathode, and this cathode is accelerating them up to what we call the velocity selector. So this velocity selector is composite, or into this velocity selector, we now have the two fields. We have the electric field and the magnetic field. So this is these two fields. They make the path of these ions to be a straight line. I hope that what we have here is going now to be ejected. I mean, these ions, they will be now ejected into what we call the vacuum chamber. And to this vacuum chamber, again, we have the magnetic field. Only this magnetic field is going now to let us have another curve. So this is going now to be the curve which is in the form of a circular, okay? Now, students, let's have now the analysis of this in terms of formula, in terms of expressions. So, I hope you have finished it out to copy this, because this is what I've told you as write down the explanations. Let's leave this one for you to continue. So when the electrons, they are ejected from the ionization chamber to the velocity selector. So what we have there is the two fields. It means that there will be into ions into the velocity selector. So we have two forces. One is the electric force, okay, and another is a magnetic force. So the electric force here will be equal to the charge times the electric field. So you see that electric field we have into the diagram. So we now have the electric field times the charge equals to the electric force. And then the magnetic force, because we have these charges moving in a straight line, and they are now reaching this magnetic field, being perpendicular to this magnetic field, okay? So this time now we have the magnetic field times the charge times the speed of this electron. And then, because these two forces, they are the only ones that act on the ions, then from Newton second law of motion, we have this is F electric field equals to magnetic field, and this gives charge E equals to magnetic field times Z charge. Then we have this gives just the speed that they enter with into the electric field number 2 there will now be equal to electric field over the magnetic field that we have. This is the expression number 1, but this is velocity. It is the velocity that they have when they enter the magnetic field into the vacuum chamber, right? Okay, students. Now, let's continue this by asking ourselves what will happen when these ions reach the vacuum chamber. So into the vacuum chamber, we have the two forces again. There are two forces. One is again the magnetic force as usual, okay? So which is equal to BQ times ZV. Now, this magnetic field into the vacuum chamber. So let's call it as B prime, because we have one magnetic field into the velocity selector, and we have another one here into the vacuum chamber. And then we have and another force will now be the centripetal force, because these ions, they are now following the circular path. And then we have the mass times v square over the radius. Then from these forces, we find what are we going now to find? So here we have this is the F equals to F centripetal, and this gives a B Q V, and this is B prime, which is equal to 1 over just to mass V square over the radius. So this radius is a radius into which we have this one follows. We have it there, okay? Do you see that? This is the radius, right? Because it is a circular path, and then we may have now the radius from the center of this, and then it is what we want now to determine, right? And then this will give us now the radius, which is equal to, that is the mv over b, then times z q. So this is what we have as the radius. Okay, students? Now, there is another way that we can now think this expression. When the electrons, they are from the ionization chamber here, and they are now accelerated to the velocity selector. So this time, we have the two energies. We have one energy is electric, let's say for the undeflected, deflected ions, we have So what we have is the electric potential energy, which has now to be transformed or is going now to be transformed into the kinetic energy. So the electrons now that are moving. And then here we have the charge times the potential difference, which is equal to 1/2 mass times V square. And then this gives the V, which is equal to 2 charge times the V, just the change, the potential difference of the mass, now square root. Okay. Now, students, I hope this velocity is the velocity for these undeflected ions. Okay? So let's now use this velocity, and then we substitute this velocity into that formula, into this expression. And then what do we find? So here we have, then here we have R will be equal to M over B Q times the square root of 2Q change over the mass. And then let's say that we are going now to square both sides. And then what do we find? We are going now to find, when we square both sides, what do we find? Students, did you finish to do that? Correct. So what we have there is the R squared, which is equal to mass squared over BQ squared here, times 2Q, they change the potential difference of the mass. And then for these ones, you end up with, you have a simplification on this one also. So this is going now to be simplified again, right? And then we have this Q is, again, closed out with this square. And then after, you see what we remain? We remain with the R square. Remember, R is the radius. You remember that? So then it equals to M over B squared times Q, because another one was closed out. And then we have 2 times the change in the potential. This is the potential difference that we have now. So what we have here, so this implies that Q over the mass from this expression, Q over the mass will now be equal to, that is the 2, then times the change in the potential, just the potential difference over the radius squared times the B squared. Now, students, I hope this expression that we came now to find is really very important. So because this expression is even what we call the charge, this is the charge to mass ratio. So this is, it means that unit for this unit is, you see that is the charge over a kilogram, and this means that we have it as a specific charge. Again, this is another way of calling it, okay? So now, students, we can now have this, after we have these expressions, we may now just use these ones again to explain the uses of mass spectrometer. We have defined it. We have now we shown how now this mass spectrometer works, and then it is the time now for us to think about what is the uses of this. Uses of mass spectrometer. Okay, so it is number one. It is used now into the analysis of the forensic. Do you understand that? This time now, we have, it is used in the forensic analysis Oh, student, what does that mean? It means that here it is used now to just to analyze the drug. Here we have the forensic analysis. This is to analyze the evidence, the abuse and the evidence, you know. So, and again, it is this time now we have it as the contamination of drugs. This is when it is for pharmaceutical use. So it is used into pharmaceutical analysis. So this means that it's just this is the discovery of drug. So discovery of drug, and another thing, like whenever they discover this COVID-19 drug, this time now they will be probably using this pharmaceutical analysis. And again, it is used to just into environmental analysis. So when they are analyzing now the soil assessment contamination, do you understand that? And again, for drinking water testing. This is another use of this mass spectrometer. Now, students, let's have some more numerical applications of what we have determined there, of this expression number 1 and expression number 2. Hope you still remember these expressions. Now, students, we have example number 1. This example number 1, a proton QP equals to, just this is the charge of the protons, and the mass of proton they are given is captured into a magnetic field of 0.110 Tesla, and the spins around a circle of radius 4.5 centimeters. Find its speed, knowing that it moves perpendicular to the field lines. Student, I give you some few seconds now to think about this question. Then we go. So what we have here is the data that we have. So I hope you finish it with this formula. And then we are going now to apply the expression, but I will leave that one in order now for you to just to remember what we have used. So here we have so the data, we have number 1, this is QP, which is equal to 1.6 times 10 to the power minus 19 coulomb, and the mass is equal to 1.6. It was given here. So 7 times 10 to the power minus 27 kilogram. And what else? The magnetic field is equal to 17 Tesla. And the last one is the radius. The radius is 4.5 times 10 to the power minus 2 meter. And then we use the expression. So that is V over BQ. And then here we can now find the speed will now be equal to RBQ over the mass. And let's substitute, and then we find 0.0, that is, let's have the radius is 4.5 times 10 to the power minus 2, okay? So this is going to be 0.107, so then times the charge times 10 to the power minus 19, all of this over the mass is 1.67 times 10 to the power minus 27. So the answer here will be in 2 meter, and then we end up having what? So please, can you calculate? You have now a minute now to finish to calculate this. No, some seconds, and then here we go. So I hope that we have calculated that we have So this is going out to be 4.6 times 10 power 5 meter over second. This is the radius. Now, students, so what we have is number 2. An operator of mass spectrometer produces a beam of doubly ionized 2 plus neon atom, the first accelerated by a potential difference of 34 volt. Then as the ion passes through a magnetic field of this value, the radius of the path is 53 millimeter, determining the mass of neon atom to the closest whole number of the proton masses. Now, students, let's have again the data. So, and then we substitute, okay? So this is for number 1, then for number 2. What do we have? Then we have, just to be quick, so remember the expression that we have used for this one. We have said that the charge mass ratio is equal to, do you remember that? Okay, students. So we said that T is equal to the potential difference over what? So what we have is the magnetic field, and again we have yes. So this is squared. So from this expression, so we have the overall data. So from this expression, we can find the mass. So what is the mass of this atom? Okay, the mass here is equal to, that is the charge, B squared R squared over the 2 change in the potential difference. And then this is going out to be substituted. So what we have here is, let's substitute. We have, this is equal to, we have 3.2, then times 10 power minus 19. You know, this 3 is the charge, because the charge is going out to be 2 times 10. No, it is, yes, it is 2. Then 6 times 10 power minus 19 coulomb. So then you find this 3.2 times 10 power minus 19. Then here times the magnetic field is 0.05 Tesla. Then you have that is, here you have, because it is now squared, the radius is what we have said to be 53. Then times 10 power minus 3, then squared again. All of this over 2, then times 30. Yes, that is 34. That is the volt. And then the mass is in kilogram. Then, students, I hope that you have finished now to calculate this mass. What did you find? I hope that you have found that the mass here equals to 3.8 times 10 power minus 26 kilogram. And then we can find the number of protons here to be equal to the mass that we find, the mass of this atom neon over just the mass of proton. So this time now there will be 3.8 times 10 power minus 26. This over 1.6 times 10 power minus 27. And when you calculate this, you find, okay, so this gives the approximate equal to 20 protons. Students, this is the end of our lesson. The homework that I'm giving you is only for 2 questions. Work on these 2 questions. By the time that you are there at home during this period, and continue with some other questions from the books, right? And then you submit the answers to your teacher and even to your colleagues. Thank you, and we'll meet you by the next time.